Hello, this is Craig Callender. I'm a philosopher of science at the University of California, San Diego. Specialize in philosophy of time and philosophy of physics, metaphysics of science. And I'm talking to...
Sean Carroll. I'm a physicist, theoretical physicist at Caltech. I am not a philosopher, although I did actually minor in philosophy as an undergraduate. And I had the great chance as a graduate student to sit in on courses by John Rawls and Robert Nozick, and so I've had a long abiding interest in it. And I've also been working on things in physics that have philosophical components like the arrow of time, the origin of time asymmetry, and also the multiverse, which you might be getting to.
Right. Oh yeah, that's right. In fact, we've been in a symposium together at the PSA on dimensionality.
That's right, the number of dimensions
Number of
of
dimensions.
space, yes.
Um,
I,
yep.
w- I
So,
w- we all had different. What was your assignment? Mine was it's more than three dimensions of space, I
oh yeah. Mine was looking at the arguments why it has to be three,
Right, okay, good.
which I
Yeah,
didn't really think
fair
those
enough.
came to too much. But anyway, today we're going to talk not about dimensionality, but the arrow of time, and thinking that that will move into a discussion of multiverses. And so we thought we'd start off with the arrow of time, for roughly the first half hour or so, and then move into multiverses. Um, so the arrow of time is a great topic. There are many different issues that arise. So philosophers thinking about it might want to distinguish right from the get-go, what they might call the direction of time from asymmetry of time from asymmetries in time. That is, some people think that time itself has a direction to it, a real stamp of, this is the future, this is the past. And it might be that they think that the future is unreal and the past is real, or the
Right.
present is real and coming into existence. But then we can distinguish from that. We can distinguish asymmetries in time, and so there are all sorts of different asymmetries. The number of McDonald's is growing. It seems each year. Number of golf.
Entropy, see, right there.
Yeah. Number of golf clubs, and then more physically interesting ones. Well, there are a bunch of ones that are important for our, the way we live our lives. The fact that we have memories going one direction. Our memories accumulate in one direction, not the other. And causation. It seems like we can cause, our actions at any particular point cause some effects downstream, that is toward the future, and not toward the past. Maybe the past backward causation is conceivable, but it doesn't seem to happen all that much, at least not on the macro scale, as far as I know. Um, and and then counterfactual dependence, which must be related to that in some way. That changes now. Will the future seems to depend counterfactually on the present in a way the past doesn't. Any of the things I do now, there's no lever I can press, no button I can press that will, lever I can pull, that button I could press that will change, where I was born.
Right.
And then there are all these physical asymmetries, this cosmological asymmetry, with the expansion of the universe, the radiation asymmetry, all these spheres of radiation outgoing, expanding, not converging onto spheres.
Mm-hmm.
And then, of course, probably the most famous of all, the thermodynamic asymmetry in time. And it's a big question of how all those different things, if they're related. Is there a master arrow unifying all of these different arrows? Or, are they individually, are they just separate and not, maybe there's not a master arrow or that. Or maybe there's a bit in, something in between. Maybe there's a master arrow, but connections between the radiation arrow and the thermodynamic arrow.
Right.
And so we're going to concentrate mostly on the thermodynamic arrow of time. I hope, and I think probably Sean hopes too, that it's connected to some of the other arrows. But whether it is or not, we will just concentrate on the thermodynamic arrow. What is the thermodynamic arrow? Well, it's it's enshrined in the second law of thermodynamics. Thermodynamics, the science that started in the 19th century, the science of steam engines and things like that. And you can put it in different ways, but it's the idea that the amount of energy usable for work is at best is shrinking, or that entropy is increasing.
Mm-hmm.
And then that theory is then was then given a new look when statistical mechanics and kinetic theory were invented. And then there are different ways of thinking about it, but people think about it in terms of entropy being a measure of the available phase space for a system. Now, philosophers might not know what phase space is, but if you think of the state space of a system, that is the not the if you think of this individuate the states, the fundamental states a system could be in. Loosely speaking, there might be more or less of these, and the entropy is a measure of this. And that was one of the great insights of Boltzmann, was linking this concept from phenomenological thermodynamics to the micro realm in terms of the number of ways a state could be. And so,
Yeah, I mean, the way that I like to say it is just the number of arrangements a system can be in without changing its macroscopic appearance, the logarithm of that number, strictly speaking. So if there's many ways you can rearrange the atoms, the entropy is high. If it's very, very delicate particular arrangement, then the entropy is low.
right, and so the reason, so it could be that if we think, classically, could be that the positions, the velocities, the initial positions and velocities of all the particles of air in my office right now, take their subsequent trajectories so that they're all in the corner of the room. The next minute, I die, and hopefully that doesn't happen, and most likely it won't, because if you think about it the way Sean just mentioned, then the number of arrangements where all of the air in my room is settled into the corner is vastly smaller than the number where it's in equilibrium and spread out throughout its available volume in the room. And so, for that reason, I won't die, hopefully. Well, not right now.
Yeah, I mean, so maybe I can just sketch out the what I think should be the standard model for thinking about the relationship of this thermodynamic arrow to cosmology. It's not the standard model because not everyone agrees with me, but I think there's some things that we do understand more or less and some things we don't. And I can just sort of mention those briefly and then we can start talking about them, unless there was something that you didn't get a chance
Go
to
right
say.
ahead.
Okay, so like Craig said, when you're low entropy, there's only a small number of configurations that look that way. When you're high entropy, there's a large number of configurations that look that way. And back in the 1870s, Boltzmann and his friends kept trying to prove, on the basis of this understanding, that entropy would go up. Because before they came along, the idea of entropy in the second law was invented before Boltzmann defined it in terms of macroscopic rearrangements. But the problem is you can't prove that entropy will always increase because the crucial element here is that the underlying laws of physics that Boltzmann would have used, or even the improved ones that we use now, because Boltzmann didn't know about quantum mechanics or relativity, but they all have the property that the underlying laws of physics are completely reversible. That as far as our best understanding of the microscopic laws of physics are concerned, there is no arrow of time. There is no difference between the future and the past. Any process that can run one way can run backwards and look the same. If you make a movie of a pendulum going back and forth and you play the movie backwards, it would still look like a good solution of the equations of motion. So what you can prove using Boltzmann's ideas is that given the entropy now, given the arrangement of stuff now, the overwhelming majority of microscopic states, individual particular states of the system that look that way, have the property that toward the future they will increase in entropy. And that's just because there's many more ways to be high entropy than to be low entropy. So if you don't know anything other than the macroscopic features of the system right now, in the future the entropy will tend to increase. That is very probabilistically likely. The problem is that exactly the same logic tells you that if you only know the features of the system today, the overwhelming majority of them traced to the past also increase in entropy. In other words, almost all of the things, almost all the ways to get to your system today came from pasts where the entropy was higher. So if you have, a half melted ice cube, you think that, okay, you predict that in the future it will melt and we'll get a cooler glass of water. In the past, we think that it probably came from a completely unmelted ice cube, and the ice cube has been melting all along. But if all you know is that you have the half melted ice cube right now and you know the fundamental laws of physics, then the overwhelming majority of microstates corresponding to that ice cube came from pasts where it was an unmelted ice cube, and this ice cube just spontaneously formed out of the glass of water. So that would be the prediction of statistical mechanics if that's all you had. We don't think that's right, therefore we think you need to do something else. In other words, Boltzmann's setup all by itself and the machinery of kinetic theory and statistical mechanics are able to give a pretty convincing argument that entropy should increase toward the future. They are not able to really explain why the entropy was lower in the past. So the standard thing one does, if you want to account for what happened in the past as well as what will happen in the future, is you just make an additional assumption. You say that it is not true that all microscopic configurations of the atoms in your glass of water are equally likely. The ones that are likely are those that are consistent with a low entropy past. So that is what David Albert called the past hypothesis, and there's a little bit of detail there going on, but the point is you put in an explicitly time asymmetric ingredient to your theory. You say that not only do you have the laws of motion, not only do you have the system today, you also have a low entropy boundary condition in the past. That's basically where, in this way of thinking about it, the asymmetry in time comes from. It's not from the physical laws underlying anything. It's not from Boltzmann's way of thinking about entropy. It's from a past boundary condition. And so then there's two challenges if you believe that whole setup. Well, of course, you could deny that setup. You could try to be contrarian about it. Maybe we'll talk about that. But even if you believe that, there's two things facing you. One is connecting the growth of entropy, as described by the second law of thermodynamics, the fact that your room gets messier over time, ice cubes melt, smoke mixes into the room and doesn't unmix. You can make eggs into omelets, but not omelets into eggs. Connecting that with all of the other noticeable asymmetries in time, the asymmetries in causation, in memory, stuff like that Craig already mentioned. So that's sort of an ongoing research project that will undoubtedly keep people busy for years to come. The other problem is explaining the past hypothesis, explaining why the early universe had a low entropy. Is it simply a brute fact that we need to accept about the universe? Is it something that comes out of the wave function of the universe, some quantum cosmology ideas, or is there some dynamical explanation for why the universe must have been that way? And so we'll talk about it in great detail, but I have my ideas, other people have their ideas. Some of us don't even agree on whether or not it's a question worth asking.
Right.
Does that
Yeah,
make
that's
sense?
right. And I think that's one of the Yeah, so we will end up, I think, agreeing on an awful lot. I think, yeah, just so the audience knows, so I think, we're both on board up to this point. And so,
Right.
I mean, I guess I do have a kind of somewhat contrarian worry about the move from all the subsystems of the universe to this, to the past. Well, I don't know. Let's call it the past state, the state of the past hypothesis predicts. That Yeah, it's not so clear to me that that's all well defined and that we can get from the system as a whole back to the subsystem. But I think maybe it's best. It'd be more interesting if we, because I think we could still then raise all the same issues about local systems and stuff, and so it might be best to bracket
Sure.
that and think more about. I think one point of of disagreement is on whether or not the past hypothesis itself needs to be explained.
Right,
Um,
that is right. And I should say there's other disagreements. We'll probably talk about this one, but it's probably the most common area, at least of confusion, when that spiel is given, is people questioning whether or not we understand enough about cosmology and gravity to even define entropy in the past when the universe was young. I mean, taken at face value, what I said implies that the entropy of the early universe is very small compared to what it could have been, and I think that that is true. There's sort of a know nothing level of objection that says you just don't know what the entropy was in the early universe because we don't understand quantum gravity enough. But I don't think that's your favorite
no,
approach.
no. I do worry about once so there's a common lore that, when you add in gravity, the formerly, high entropy was a spread out state, and then you say, well, with gravity, it's attractive rather than repulsive, and so we should think of it as clumpy state is the new high entropy state. So
Hmm.
clumpiness is the new anti-clumpiness, and vice versa. I think that's sometimes a bit too quick, and I'm not. There's a literature on gravitational statistical mechanics. Even just classical, just
Right, just
just
Newtonian.
Newtonian.
Yeah.
It's really there are a lot of open questions there, and so I'm a little bit hesitant to, I don't know, just completely sign on. But on the other hand, I would agree ultimately that some kind of special state is going to be needed to be posited for all this to work. So,
Hmm.
and those objections are maybe more just kind of technical. So maybe it's better to concentrate on the whether it needs to be whether granted that it is granted that you're going to posit let's assume a positive past hypothesis. Does it then call out for explanation?
Right.
Um,
So now I'm being the establishment and you're being
yeah,
critical,
so I
right?
think so in physics, it does definitely would seem that I would be the rebel here. In the physics community, it seems it's not something idiosyncratic to you by any means. Many people I've seen even somebody list top 10 unsolved problems, and you know you can guarantee that explaining this low entropy or initial state is always rises to the top 10 somewhere. Um,
I'm not actually completely convinced. We probably shouldn't talk about this too much because it's a sociology question. But I actually, if that were true, I would be delighted. But I have had to really try to convince a lot of
all
my
right, well,
colleagues that
that's
this is
interesting.
an important problem that we need
That
to
probably
address.
says more about the circles I
I mean,
travel in.
far too many, yeah, I mean, far too many people say, but of course the early universe had a low entropy because that's what the second law says,
I see.
which a little backwards in my mind. But
Um,
anyway,
yeah, so I guess one little bit of setup then so when we talk about the past hypothesis, what is the past hypothesis? It's the idea that the initial entropy is low. You're not building an initial; we're just saying one end is low, and that's the end that we call the past.
sure.
Um, and what do we mean? Well, with it, well, if we're thinking classically, then of course there are a continuous number of microstates there, and so what we're doing is slapping a probability measure over the to get this whole Boltzmann thing working. We've got to slap this probability measure over the space of all states, and then we're restricting so the initial we're restricting the initial states to some subset of this state space, and then then that's going to make and then given the probability measure, it's going to make subsequent transitions are going to be the likely ones are going to be the ones of the entropy increasing. Um,
Right. I mean, just to be clear, there is a measure mathematically, either in classical mechanics or quantum mechanics, and then the that it's a measure and it's kind of uniquely defined given the symmetries of the theory. The question is, to what extent is that a probability in any sense? Does that help you define the likelihood of
right.
something?
Yeah, I myself don't have a problem saying it's a probability. But well, here let me just say. Well, so okay, so I'm going to be on the skeptic side here about whether or not to
Right.
explain this, and I guess I think, well, I don't want to sound like I've got the master plan for the future of science, and so people can go and try to explain things
Right.
what they want to explain, but thinking that it needs to be explained or has to be explained. Notice first of all that once you've restricted, when you restrict to those states, you're putting the uniform probability measure over those states, and so although intuitively it seems surprising that those states are the you know why did the universe start off that way? So it seems surprising why did it start off that way. But it's not that the theory is itself saying it's unlikely that it started off that way. In fact, if you think of that past hypothesis as a kind of nomological, law-like supplement, then it's probably one that started off in that set of states. And so it's a bit like, so I think of it like, when you think that energy is conserved. So you take the set of states, which if it's classical is 6n dimensional, and then you restrict to an energy hypersurface, so then it's 6n minus 1 dimensional. And you don't say to yourself, well, it's really improbable that I'm on that energy hypersurface. Well, no, because the probability is defined right over that, just on that surface. And so now I'm thinking the similar sort of thing, but now I'm constraining it to some subset of that, and smearing out the probability over that, and then thinking, well, the probability is just one of that happening. So what's the mystery?
Right. So I'll give my working physicist's point of view on that. I always try, when I'm being intellectually honest, to admit that it is always possible that there is no explanation for this. This is a fact about the universe, and it's certainly not clear, as a theoretical physicist, what things there are to be explained and what things are just accidents or brute facts. I mean, back in the day, the number of planets in the solar system was just the crucial number we had to explain on the basis of platonic solids or something like that. And now we know better because we have a better theory. The number of planets is just kind of an accident. Different solar systems will have different planets, etc. So it might be the case. Having said that, in this measure that exists on the space of all possible states, the fraction that looked like the early universe is incredibly, incredibly, incredibly tiny. Roughly speaking, 1 part in 10 to the 10 to the 120. So if it's an accident, or if it's just a fact, it's a really big accident. It's a very noticeable fact about all the possible, about the actual way the universe started versus all the possible ways. But more importantly, I think that whether or not we take the low entropy of the early universe as a fact to be explained, there still is the mystery of what happened in the early universe. The Big Bang is not something that is completely accommodated in our current theories. It's a place where our knowledge gives out. General relativity is not good enough at the Big Bang to describe what happened. We need a better theory, presumably a quantum mechanical theory of gravity, but at the very least some other theory that is going on that would actually tell us what happened at the Big Bang. Is it the beginning of the universe? Is it a phase the universe goes through, or whatever? And so, given that we do need to know what happened at the Big Bang, there's no option of just saying, I don't know, something happened, because we don't even know what that thing would be. To me, given that state of affairs, the fact that the conditions near the Big Bang were so peculiar, were so specific and ungeneric in the space of all possible states that the universe could have been in at that time, that's a tremendous clue to us. Trying to understand the Big Bang, and you're saying, well, there's this thing we don't understand, and it's very, 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 very special and non-generic in the following way. The attitude of saying, well, let's just accept that. Let's not try to explain it. It's not worth trying to invent complicated mechanisms to account for that fact. Just seems to be, counterproductive scientifically. It may be true that there's no explanation for the low entropy of the early universe, but it's probably the single most blatant feature that we have of this part of the universe that we don't yet understand. So maybe by trying to come up with models that account for that dynamically and naturally, we will get better ideas about what happened at the Big Bang. It's an empirical question, and like you say, we're not here to be the police telling people what to care about and what not to care about. But my money is on trying to explain the low entropy of the early universe will lead us to other things that we'd like to explain.
Yeah, just to connect up with that, yes, maybe my view is in the minority here, but I am thinking that the way I'm coming at is okay. I'm trying to make sense of thermodynamics and it's sitting on mechanics, but and then the logic of that is then pushing me to the past hypothesis. It's
Mm-hmm.
then I'm thinking of that as ruling out. So once I make it, I'm thinking of it as ruling out from the space of physically possible universes, one's not like that didn't start off that way. And so the surprise, so in a way, the phenomenon that stimulates the way the train of thought you're having, I'm sort of trying to pull the rug out from at the beginning by saying, that's the only way it could have been. So in the space, so when you say that it's a very, very surprising sort of state in the space of all possible universes. Well, for me, the space of all possible universes is just those that started off with the past hypothesis.
Yeah, I mean, and again,
I,
I'm not quite sure what to say, except that could be true. That could be the way it is. But just to emphasize, that is not the only
no,
possible
no, I
explanation
agree, and
for
definitely, if
yeah
you're
for
coming
what
at
we're in right
things
now.
from okay, I know that it's going to be quantum gravity, and I know I've got to come up with a new theory. Um, and then when you come up with a new theory, you are trying to look at for that. Then the way I think about it, when you try and come up with a new theory, then I'm not a big fan of thinking that there is, the scientific method. I must say, and I think, if you look at the history of science, you just see all sorts of things, have worked, and people
Yeah.
follow different intuitions and hunches, and sometimes it works out, sometimes it doesn't. And so, like, so I'm not here to be a, kind of thought police in any way. Um,
You totally aren't. I can admit it.
but yeah, so if you're coming at it from, and so then people will find different things in current theory that they hope that with a new theory they'll be able to explain. And so when people look at the standard model in quantum field theory, and Weinberg will talk about all the 17 independently adjustable knobs, so all these
Yeah.
different values, which it'd be nice if some other theory predicted precisely those things rather than leaving those up
Mm-hmm.
for grabs. And the entropy thing might be like that. One thought about it though is that if you're keeping a kind of Boltzmannian picture, the way I think about it sometimes is that, well, what would explain the low entropy state? And maybe this is a good way to segue into your theory. Until starting to think about multiverses and things like this, I would, if we're just sticking with one universe, I would think, well, the one thing that would explain the low entropy state would be before it would be in, an even lower entropy state, and et cetera, et cetera, et cetera.
Right. No, well, that is
In which case,
yeah.
then it doesn't seem like there's any gain. You just put, the bump in the rug is popping up, you're stepping on it, and then it's, going back a step.
No, I definitely think that if that were it, that would be highly, in other words, in the world we have right now, the way we explain the fact that the entropy of the universe was lower yesterday than today is to say, well, because it was lower the day before yesterday. And that goes all the way back to the Big Bang, and then we hit an edge. We don't know what to say. And so it's possible that you just keep going. And actually, a lot of the cyclic universe models or bouncing universe cosmologies actually do this. They just basically say you keep going forever. The Big Bang is not
Mm-hmm.
an edge. You go to the past and past and past, and the entropy of a co-moving region of the universe just decreases forever. And I find that incredibly unsatisfying myself. Um, but it could be true. So let me just say, because I think it's possibly helpful to discuss one of Boltzmann's scenarios. I mean, he was aware of this problem in the 1890s. He returned to it somewhat carefully, And like I said, early on, he was trying to prove that entropy had to go up, and then he realized, well, you need some extra ingredient, and he was not very clear on what that ingredient was. One of his scenarios was just to say the universe is eternal, and usually it's in thermal equilibrium. So thermal equilibrium will be the highest entropy state you could be in. For if you ignore gravity just for the moment, then it's just uniform gas in a box of gas or something like that. And Boltzmann didn't know about the Big Bang or general relativity, so he believed in Newtonian space-time. And if you live in a Newtonian space-time that is there forever, it's eternal, and it's full of atoms that are just bouncing into each other, most of the time you'll be in thermal equilibrium. Most of the time you'll be in a maximum entropy state. But because he's Boltzmann and he knows that entropy is a statistical statement, not an absolute one, he knows that in that configuration, if you wait long enough, the entropy will go down, just as a fluctuation. The air molecules in your room will eventually all go into the corner and you would die. But if you run the numbers, the time it takes for this to happen is typically much, much larger than the age of the universe. But Boltzmann says, but you have forever to wait if it's the whole universe you're talking about. So eventually you will fluctuate into low entropy configurations. And so he says maybe our galaxy is such a fluctuation. Maybe everything we see, the 100 billion stars that we now think are in the Milky Way, it's all just random motions of the molecules that are usually in thermal equilibrium fluctuating into lower entropy configurations. And this happens not just once, but it happens an infinite number of times all over the place. So he invents what we would now call the multiverse. He says there's universes mostly in thermal equilibrium, but there's little patches where you fluctuate into low entropy configuration and then you bounce back. And the reason why you care about this is because when you're in thermal equilibrium, you can't live there. Life itself is impossible. It depends on an entropy gradient. So he invokes what we would now call the anthropic principle and says that in this thermal equilibrium ensemble, we will live in the low entropy regions. That's why we do. And this is a pretty good theory, actually. It sort of doesn't cheat. It doesn't sneak in any time asymmetries by hand. It derives them dynamically, and it makes falsifiable predictions. And sadly, for this theory, the predictions it makes have been falsified, which is why we don't believe it, besides the fact that the universe is not Newtonian. But so Eddington in the 30s then comes along and says, if you believe this, it's true that there will be fluctuations into low entropy states. You will get something like our galaxy, but you don't need a galaxy to explain us, right? You need a much, much more mild fluctuation in entropy to explain us rather than to get the whole galaxy. And now we would have 100 billion galaxies that we need to explain. You could just get the solar system, right? That could fluctuate randomly into existence. Or you could just get a person. Or we would now say you could just get a brain, a configuration of atoms that was right in the correct arrangement to have a thought, and that thought would be, oh, look, I'm in thermal equilibrium, and then it would dissolve back into the primordial chaos around it. So that's what we call a Boltzmann brain, and the prediction of Boltzmann scenarios that most intelligent observers are Boltzmann brains. And there's actually great philosophy questions to be discussed about how do you know that you're not a Boltzmann brain, but in the end, I think they all conclude by saying we know that we're not, and therefore you need to do better. And this is a great example, I think, of that's a theory without an explicit past hypothesis. The universe is time symmetric overall. There's just as many downward fluctuations as upward fluctuations in entropy. But it doesn't work. It doesn't fit the data. So as contemporary cosmologists, we need to come up with some theory that has the good properties axiomatically that one does, but that predicts that we live in a nice, hospitable universe with 100 billion galaxies in it that started with the Big Bang.
I was just going to interject and say, theories like the Boltzmann's brain picture are my colleague up the road, Jeff Barrett at Irvine, calls, well, in a different context, but empirically incoherent theories. So they're theories that,
Yes.
if they're true, and they could be true, but the evidence, but then all the evidence you have is not evidence for the, if you were just a Boltzmann brain, then everything you took to be evidence for the theory that would lead you to believe that would not be actually evidence for the theory.
That's right, yeah. So, I mean, one way of saying why it doesn't work, which is not quite right, is to say that given that the universe fluctuated into the room that you're in right now, with your memories and with your impressions of what the external world is, the overwhelming majority of times that it would do that, outside your room, it's still thermal equilibrium. So you open the
Mm.
door and you realize that, oh, it's not right. But then you think about it carefully and you realize, but okay, of all the ways that you could fluctuate into, a person who walked outside the room and see it is not thermal equilibrium, most of them are in fact thermal equilibrium outside that immediate horizon. So you can't
Hmm.
disprove on a simple empirical basis that you're not a random fluctuation out of the chaos, but like you say, it's not a productive
Yeah.
way to get through your life. The phrase that I used was cognitively
Yeah, that's
unstable.
that's good.
You can't think about it in a sensible way. And it's in that sense it's like being, a brain in a
Yeah.
vat, or, being teased by a Cartesian evil demon, right? Maybe that's true, but it's
No.
no way to live your life.
um, well, that would be a natural way to move into your theory. Do you want to give that?
Sure. If you would like to call it a theory, it's a proposal. So the inspiration for my idea is the following: that um, we say that low entropy configurations of stuff are a small fraction of all the possible arrangements you could have. For example, an unbroken egg, is very low entropy compared to scrambled eggs. It's a small number of arrangements that are as orderly as the shell and the egg white and the yolk. And yet, when you open your refrigerator, you are not surprised to find unbroken eggs in there. It is not. You don't say, "Oh my goodness, why isn't that in a higher entropy configuration?" And the reason why is because the egg is not a closed system, right? It came from a chicken, and the chicken is embedded in an environment that is very, very far away from thermal equilibrium. So my own proposal that I wrote up in a paper a couple of years ago with the student Jennifer Chen was that our universe is like the chicken. There is a universal chicken. We are not alone. The universe is not a closed system. We were born out of another universe. And that's not certainly an original idea to us. The spin on it that is somewhat original is we imagine that the original universe is high entropy, that there's no fine tuning or special state that corresponds to the universe out of which we came. And so the whole trick of this scenario is to ask, how can you create a low entropy Big Bang out of a high entropy pre existing universe? And there, I think that the secret is the discovery in 1998 that our universe is accelerating, indicating that there is a vacuum energy, a cosmological constant. And there's a long story here, but to make it short, if there's a vacuum energy in empty space, then there are fluctuations in empty space. There are quantum fluctuations according to Hawking and Gibbons. And so even empty space, if there's vacuum energy, is not completely quiet. It's not quiescent. It just doesn't sit there. The quantum fields that make up the universe gently fluctuate. And among those fields is the gravitational field, the curvature of space-time itself. So the hypothesis, which is very far from being completely well-founded, but at least is not completely crazy, is that you start with empty space, nothing in it, nothing but vacuum energy. That would be the high entropy state. That is a static configuration. It doesn't change in any way. But there are quantum fluctuations, and among those quantum fluctuations, you can create not only an atom here or there, or a brain or a solar system, you can create a tiny little bubble that pinches off and becomes a baby universe. It then expands all by itself and gets its own entropy that adds to the entropy of the original configuration. So, if this scenario makes sense, the way that it's winning is that when you make a whole new universe, it's easiest to make a small universe and therefore a low entropy one, rather than to make a big universe from scratch. So, even though low entropy configurations are rare, they would be easier to make in this scenario. But of course, if you believe that, then you believe it's not going to happen just once; it's going to happen an infinite number of times. So we are a baby universe that is part of a much bigger ensemble with an infinite number of other sibling universes, and then you're faced with a very difficult problem of calculating probabilities, trying to figure out what your universe should look like, and connecting it ultimately with features we can measure here in the universe we live in.
Right. Uh, yeah. Yeah, that's the proposal in that paper, and that's certainly novel to we philosophers, I think, who had been thinking about this issue. Um, and well, this takes us into the multiverse a little bit. Well, quite a bit, I guess. Um, but let me ask. I mean, to me, I guess when I think this isn't a, I don't know, I don't know how what kind of comment this is really, but it just seems very striking that so much unobservable, in principle, unobservable stuff is being posited, uh, to sort of to scratch this itch, to explain this past state. I mean, it just, I don't know. If you think of scientific theorizing as trying to give simple descriptions of the world. If I think of the laws as giving us kind of summaries of the world, and this is adding on so much complexity to the theory, and you know, I don't know exactly how to measure these things, but am I getting back enough in return, and how can I be sure that I'm not going to end up having just as many questions, just like I have about the past hypothesis, but when all the details are filled in this theory, that similar sorts of questions won't arise. I wonder.
Yeah, no, I mean, I think these are all very fair questions, but I think that it's very similar for the first part of that question about, how much am I adding to my scientific theory? It's very similar to the state of affairs in the many worlds interpretation of quantum mechanics. People who don't like the many worlds interpretation say, "Look, you're adding this huge number of worlds and saying that there's splittings going on all the time. This is a tremendous ontological burden." And people who like it say, "Who cares how many worlds you're adding? You're decreasing the number of equations in your theory. Instead of having two forms of dynamics in quantum mechanics, unitary evolution and wave function collapse, you only have one form of evolution, unitary evolution according to the Schrodinger equation." And yet another, a simpler analogy would be, which do you think is simpler? The set of integers between 1 and 375,695, or the set of integers between 1 and infinity? I think that the set of all integers, plus and positive and negative for that matter, is actually simpler than some set between two hard to specify numbers, even though there's a lot more integers there. Likewise, I would think that a multiverse should not be thought of as a theory. The multiverse is a prediction that comes out of a certain set of dynamical laws, or doesn't. So the point is, do the laws of physics, as we hope to understand them but don't yet, do they predict that multiverses should exist? Does our understanding of gravity plus quantum mechanics lead us naturally to this picture where multiverses are created? If that's true, if they do, then I think that the way to judge the simplicity of that theory is on the basis of its dynamical laws, not on the basis of how big a universe it predicts. I can only say that in a very tentative way because we don't have those dynamical laws yet, but I think that would be the goal. The goal would be to explain this enormous fine-tuning in the actual early universe that we live in on the basis of a very small number of physical principles that would predict indeed that our universe is not unique, that it's just part of one of a large number. So I'm not sure what the right way to measure the simplicity of theories would be, but that would be
Yeah,
my
neither am I.
way that I would advocate doing it.
Well, that takes us really right into the one of the issues with the multiverse, and I have to admit, I really do not like all this multiversing.
You can admit that. You're
What's
not
that?
alone there, yeah.
Yeah,
You're not alone
I'm
there,
really
that's for sure.
against it, and I guess I think maybe it would be worth saying for a minute why, because I think
Sure.
my reasons are maybe slightly different than what's often expressed. So sometimes people are, well, I mean, prima facie, there is a kind of a gulp you have to take when you think about that. I mean, if I were to posit, if I were to say to you, I mean, because the multiverses are, well, I guess the baby universe, these pocket universes are not. I mean, they're causally disconnected from our pocket universe.
That's the idea, yeah.
But they're not. I guess this pinching. If the pinching were described, then that would be some kind of causal connection to the mother universe.
Right.
So I mean, so one line of objection, what might be, worrying about its these other pocket universe, science positing so much in principle unobservable stuff. So, I mean, this is not my objection, but I mean, I think there is something, at least to the sort of the feeling in the gut, where, if I said to you that there was, some purple monster, in my room, you'd say where, and I'd say, well, it doesn't reflect light, so you can't see. And then you pull out various instruments, and I say, well, put those away. It doesn't couple to the gravitational field or the electromagnetic field. And at a certain point, you would start to say, well, why the heck should I believe in that thing? Um,
Yeah. What did it
well, that's
explain
the thing.
about the
Yeah. So then
condition of the world?
it's really all hanging on the explanation. And so, since I'm not a
Hmm.
positivist, I don't object to the positing of unseen things. Uh, if they, you know, overall contribute to a better explanation of the data than otherwise. And so we'll never see quarks because of isolated quarks because of
Right.
confinement. Yet that theory is elegantly summarizes so much data that there's good reason to believe it, I think. Um, but really, my objection is more about fine tuning and whether it's well defined. So I guess we
Hmm.
could. I mean, there's different issues, and I don't want to put on you, defending everything in all of physics on multiverses. But there's a lot of stuff on life, for instance. So I just
Right.
read that new Hawking book, and there are many other books talking about life and how it's all fine tuned. And I just don't think and this is my main objection really is that I just don't think that this is well defined. So I don't think that there's a theory of so when people say, well, if I just it's just this much of a change in the strength of gravity and then there would be no life, or just this much of a change in whatever and then there would be no life. I don't think that that's well defined. I don't think we have a theory of all of that. I mean, so to get that kind of
Right.
claim, you would need a theory of all these different ranges of strengths of gravity, or a theory of whatever the parameter is you're looking at, uh,
And you need
a
a theory
theory
of
of life,
life.
yes, a probability measure over those things, uh, and I think for other reasons which I could go into, but I think the probability measure is going to go hand in hand with the in the theorizing with the laws, um, and so I don't think that we have those things, the theory or the probability measure, um, and uh, and then further, so even if you did come up with good ones, then it seems like there's a big difference between those probability measures and the one in statistical mechanics, because the one in statistical mechanics is indirectly, but intimately connected with empirical frequencies. Whereas until you start seeing, you know, the frequencies of, maybe this is getting more toward the empiricist objection, but until you start seeing the pocket universes, you don't have the frequencies of the pocket universes. I guess maybe you might say that you get the frequencies from the theory of vacuum fluctuations. Uh,
Well, I think that no, I mean, I think that this is a very good case where the problem of the low entropy of the early universe is really very different from the problem of the fine tuning of coupling constants, and it's a better problem in some sense. It's a much more well-defined problem because I
I
think,
think that's
like you
right.
say, we don't have any measure for the set of coupling constants, and we don't know under what circumstances life would exist. And so I'm completely with you in being highly suspicious of claims that this or that feature of our universe around us has the properties it does because otherwise life could not exist. We don't know enough on either side of that argument to really make that sensible. But when it comes to entropy, I think the situation is completely reversed. For one thing, the entropy of the early universe is much, much, much lower than it needs to be for life to exist. So no one can argue that there's some anthropic justification for why the entropy is that low. And secondly, we do have a
Mm-hmm.
measure on the space of configurations of the universe. If you believe we can calculate the entropy, then you believe we know what the measure is. You can argue whether that should be some probability measure, but I mean, why not? It is the measure that is defined there, and I think that the burden is the other way around. Unless you have some better theory of what the probability measure should be, you should use the measure that's given to you by the structure of the dynamics, which is what we do when we do entropy. So that's why I'm much more ready to believe that the low entropy of the early universe is a good reason to contemplate multiverse explanations than I am the fine structure constant or the strength of gravity or the cosmological constant are good reasons to contemplate multiverse
I see.
explanations.
Okay, I didn't. That's interesting because I was sort of thinking people were
And that puts me in the minority,
lumping
true, yeah.
everyone together, but really, that I think that's right. That with entropy, at least you have. Well, I don't know if you have like well-defined measure and you get to fancier physics, but certainly classically and quantum mechanically you do. Um,
Yeah, that's right.
and so then it takes and it's motivated. I mean, it's not just a measure, um, that you've just pulled out from thin air, but it's a
Right.
motivated measure. Um,
Yes.
that's right. So then I guess the issue then really then hangs more on the earlier disagreement about whether that whether that state, the past state, is itself improbable. Since I'm putting that measure only over that, I mean, since I'm thinking of that past that the past hypothesis as a nomological restriction, then
Mm-hmm.
I'm just deleting all those possible worlds, just like I deleted all the ones with in the rest of the 6n dimensional space that didn't have the right energy. Um,
Mm-hmm. Well, I think there's two things. I mean, one is that that's why I don't use the word improbable when referring to the initial state. It is finely tuned. It's very very low measure in the space of all possible configurations you could have had. It's not improbable because it happened. The probability
mm,
is one, like you said. So I don't think probable is the right word to use. It's unusual, and the question is, does that unusualness demand some explanation? The other thing, which is a higher level concern, which is a bit harder to know how seriously to take it, but remember, we had the scenario from Boltzmann that the universe lasts forever. There are thermal fluctuations, and the objection to that by Eddington and also Feynman and other people that we should be very small fluctuation in entropy, and therefore we would not have all this complicated stuff around us. Well, it turns out if you believe that the reason why the universe is accelerating, is observed to accelerate, is that there's vacuum energy, then, like we said, that vacuum energy gives rise to thermal fluctuations. And the universe is not going to recollapse if this lasts forever, which is the simplest possible theory. So, in the future, our universe in which we live will be empty space with thermal fluctuations forever for an infinite number of years. And so, if that's true, there should be fluctuations of, virtual particles out of the nothingness that come together to form atoms and molecules and brains and solar systems. And it's very, very rare. It doesn't happen very often, but it will eventually happen. You can calculate the relative probabilities. And the number of observers like you and me who exist in the far, far future as a result of random fluctuations out of the vacuum is naively much, much larger than the number of observers like us today in the aftermath of the Big Bang. So this Boltzmann brain problem is not just a problem of this 1895 theory that Boltzmann had in a Newtonian framework. It's a problem that seems to be associated with the most popular current cosmological model. And there's different ways to get out of that. Maybe the vacuum energy doesn't last forever. Maybe we don't understand thermal fluctuations. Maybe there's something we don't understand about frequencies or counting or something like that. But maybe it's that our universe is not the whole story. Maybe we're in a part of a bigger ensemble and we're not doing the counting correctly. So I think that at least it's not obviously okay to just say, well, the early universe had low entropy. I think that there might be yet another problem you have to face with the future of the universe, not
I
just with the
see.
past.
Um, yeah, I guess I'm not. Well, I don't know if I'm on board with the most popular theory. But I'm not. Well, uh, so we're talking about eternal inflation. Is that what you're? Well,
Well, not inflation. Eternal,
just that
just that
the
our
it would just
future.
that. Okay, I
Just
see
the
that.
very tiny amount of vacuum energy that we've observed, 10 to the minus 8 ergs per cubic centimeter. If we extrapolate our current favorite model of the universe toward the future, it won't recollapse. It will empty out. Black holes will evaporate. Stars will, burn out and decay and so forth, and there'll be nothing but empty space forever, with thermal fluctuations at a temperature of 10 to the minus 33 electron volts or something like that. Some very absurdly tiny temperature, but they last forever. So you'll get fluctuations into all sorts of things. And why aren't we there? Why do we live in the warm, comfy aftermath of the Big Bang rather than the cold, forbidding emptiness of the future? That's a question that we don't have any clear answer to. One person or another might think they have a
Mhm.
favorite answer, but there's no obvious consensus solution to
No,
this
that's a
problem.
good point. That's something for me to think about, really. So maybe, yeah, we'll have this conversation again.
Once you figure it out, let me know. Yeah, that'd be very, because
uh,
I'd be
I,
curious. Yes, and let me be very very fair. Even if my scenario is right, even if our Big Bang came as the result of a baby universe fluctuation out of some pre-existing space-time, that gives you hope that you could address this problem, but doesn't obviously answer it. It's more complicated than that. You will fluctuate into both isolated brains or solar systems and into baby universes. And so you need to convince me that I need to convince you rather that I can count one versus the other and make some sense of that counting and make some statement like in this multiverse ensemble most appearances of configurations like me are associated with universes not randomly appearing out
mhm,
of the gloom. And I don't know how to do that yet. I'm not even sure if it's
right.
possible.
Um, well, yeah. So that's so I've got future study, and you've got future homework
We
work
have
to do.
homework.
uh, well, maybe that's a natural place to end things. Um, I don't know. What do you think?
Yeah, I think so. I mean, I think I like thinking about these things because, just to go back to where we started, the arrow of time is so deeply ingrained in how we think about the universe, right, and how we live our everyday lives, that there's a certain amount of effort that it takes just to convince people that there is something to be explained, right, that there is something to be thought about. And the deep down laws of physics don't have an arrow of time, but our everyday universe does. So I think this is a clue. I think it's the most blatant, in your face fact that we observe about the universe around us that we don't have a good explanation for. And so you might be right. The explanation might be that that's just a fact that it is that way, but it would break my heart if that turns out to be right. It would seem like such a shame if there weren't some deeper truth that was
Yeah,
pointing to.
I just get very nervous about big mother hen universes and that aren't like ours. And
Fair enough.
if I see that as the
Fair enough.
answer, I wonder what the question is. And so that's.
Well, sometimes in trying to make people feel better about multiverses, I say imagine that there were astronomers who lived on a planet that had absolutely 100% cloud cover every day, so you couldn't see the sky. And to them, the universe would be the world, right? The Earth, whatever they lived on, fog planet. And some person who said, well, maybe there's a large number of other planets would be a heretic that was talking about unobservable things. On the other hand, that heretic would have a tough time getting it right. It's one thing to say, well, maybe there's a large number of other planets. It would be very hard to invent galaxies and the Big Bang model if you couldn't
Mhm.
see the sky, right? If you couldn't see past your atmosphere. So even if something like this is necessary, it's really, really hard to imagine getting it right. That's no reason not to try, but it's a reason to be at least, if you're interested in this kind of thing, at least to be a little bit
In
patient.
fact, that sort of scenario isn't that what will happen with expansion? That eventually the stars will start to blink out as
Well, it does happen in the sense that,
horizons will
because,
develop from the
yeah,
expansion.
there's a cosmic microwave background. There's a point past which we can't see. So the microwave background for us is like an atmosphere that we can't see. That's why you can't see the other parts of
Hmm.
the multiverse. And the question is, is the simplest thing to say that what you see is all there is, or is that somehow very presumptuous in expanding your local parochial point of view and saying that must apply throughout the whole cosmos? I don't know.
Yeah,
We'll have to think
and
about it.
well, I'm just so happy that physicists like you are thinking about this. When I started graduate school and working on the direction of time, this was when Hugh Price was complaining about everyone making a temporal double
Right.
standard, and so it's just
That's right. Yes.
really wonderful to see physicists thinking through the the logic of this problem all the way through and thinking about Boltzmann's brains and all of this kind of thing. It's just really excellent.
Yeah, it's still a minority of us who care about it, but I think that we're gaining ground.
Well, more power to you.
All right. Well, very good, Craig.
Okay,
Thanks for the
thanks very much.
conversation.
Bye bye.
We'll talk to you later. Bye bye.